So connecting with the previous lecture, we have already discussed how to construct X bar chart, P bar chart, R bar chart and C chart. And I also show you the use of Q1 macros, which is a reliable software for Six Sigma. So in today's lecture, I'm just going to show you that how you will check that if a process is capable or not. So in my previous lecture, I have already discussed a little bit about the sigma. That means sigma is basically showing you the spread. So deviation from the mean. So if your organization want to maintain a 3 sigma, okay, so how you will check the quality measure is the product or the service quality which your organization provide, or if your organization is producing, is it meet 3 sigma, 2 sigma, 4 sigma, 5 sigma, so 6 sigma. So 6 sigma is the highest peak of the quality. It's mean good quality product. It's mean good quality services. So now in this lecture, I'm just going to show you that how you will check the capability, how you will check the quality of a specific product, of a specific service, is it meet it or not. So I will discuss some simple example, but before going to that, I want to discuss a little bit the capability process. So process capability refer to the ability of a process to produce product or provide services capable of meeting the specifications set by the customer or designer. So I mean every designer, for example, if a specific company want to produce some specific light bulbs, some specific mobile phone, so they already design the quality, they already design the structure of their product. So they already mention each and everything in the design phase. So should it will be able to maintain that quality which they design. So now we need to check that while using some specific indicator. These indicators will tell us that is that specific organization product are capable, they meet the design specification, they meet the quality measure for which they define that we are producing 3 sigma level quality, we are using 4 sigma. So process capability and indices will show you that is it capable to meet that or not. Process capability compare the output of an in control process to the specification limit. So basically in the process capability we will construct an upper bound and lower bound, just like we already discussed in the X bar chart and R bar chart. We already constructed central line, upper control line and lower control line. Then in the quality inspector example, as he visited to the Coca Fits company and she checked that the drink, the amount of drink they put it in the bottle meet the design specification what they claim for or not. So now we will check that process capability compare the output of an in control process to the specification limit. The comparison is made by forming the ratio of the spread between the process specification. The specification to the spread of the process value is measured by the process standard deviation. So once again, the standard deviation will be playing a very important role. If the value of standard deviation is very high, then the spread will also be very high. If the standard deviation is low, it means the process will be incapable. Maybe it will meet the process capability or not. But if this is a good sign, if the standard deviation value is low, it means the process will be capable. If the deviation, if the distance from the mean is very high, so in that case, it will be a little bit risky. A capable process is one where almost all measurements fall inside the specification limit. So we will call that a specification limit, just like we already discussed in the control chart, that if all the observation lies in the feasible region means between the under the upper control limit and the lower control limit, then we will give them a green signal. We will say that their product, their service quality is good. They are capable. So now I'm just going to show you with this simple example in which we have just draw a normal distribution. So in this lecture I'm also going to show you that how you will sketch a normal distribution while using Q1 macros. So after that you will be able to design this. We will also construct the upper control limit and lower control limit, and then the software will also calculate CP and CPK value. So in the coming slide I will tell you that what is CP and what is CP. CP and CPK are two different indicators. CPK is basically CP actually using the measure of dispersion, while it's not measuring the variation in the mean, while CPK also measure the variation occurred in the mean. So for this purpose, CP and CPK are different from one another. CPK can never exceed CP. So please remember this point. CPK can never ever exceed CP, and CP is just an upper bound for CPA. So in this example, this is just a normal distribution. So you can see all the bars of histogram. This is basically the histogram, and we just construct a normal distribution, are all lying between this. So the mean of this is 75. So in normal distribution, mean, median and mode lie at the same place. Because it's a symmetric distribution, so we will construct a symmetric distribution. 75 is the mean, and standard deviation in this example 0.3. Upper specification limit is 73, and this is the upper specification limit, and this is the lower specification limit. So let me correct this. This is lower specification limit, and which is 73, and this is the upper specification limit, and our standard deviation is 0.3. So 6 multiplied by 0.3 will be, so 6 standard deviation will be 6 multiplied by 0.3 will be 1.8. So when you construct, because as I already mentioned to you that how much area will be lying between plus 1 6 sigma, plus 1 sigma, plus 1 sigma, minus 1 sigma, plus 2 sigma, this will be minus 2 sigma, and plus 2 sigma, plus 3 sigma, plus 4 sigma, plus 5 sigma, and this will be 6 sigma, plus 6 sigma. Similarly, this will be minus 3 sigma, minus 4 sigma, minus 5 sigma, and this will be minus 6 sigma. So when you calculate these levels, so how we will calculate this? Because this is adding with the mean. So 75 plus, let me calculate this for 1 sigma. So 1 into 0.3, it will be 75.3. Okay, similarly this will be 75 minus 1 into 0.3. So it will be further reduced. So similarly when we construct this, you can see 75 plus 1.8. So it will be 76.8. Similarly, mu minus 6 sigma, 75 minus 6 into sigma, sigma value is 0.3. So 0.3, 6 into 0.3, it will be 1 by 8. So 75 minus 1 by 8 will be 73.3. So this is basically our 6 sigma defined zone. So now you need to check, because this is a normal distribution and these are the asymptote. These are the asymptote. It will never ever touch this line. It will be going to the infinity, minus infinity, and on this side it will be going to plus infinity, but it will never ever touch this line because these are the asymptotes. So now we need to check, is the process capable? So yes, we can see that the process is capable. So for this purpose, we already calculate 6 sigma on each side of the mean to the specification limit. So these asymptotes will be coming toward this side. I just drawing it, okay, but it will never ever touch this line. So it will be going on. So now we can see that the process is capable for CP, and you know that CP formulation is, which I will also discuss, that what is CP and what is CPK. So CP, upper specification limit minus lower specification limit divided by 6 sigma. So upper specification limit is 77 in this example, lower specification limit is 73 in this example, and our 6 sigma, 6 standard deviation is 1.8, which is 2.2. So I will tell you that when the CP value is greater than 1, then the process is capable. CP value is greater than 1, then we will consider that the process, it will be greater than or equal to 1, then the process will be considered as capable. And because we have checked it for, so for 6 sigma the process is capable, because when the value is equal to 2, then we will say that this process is capable for 6 sigma. If this value lie between 2 and 1, then we will say this process is not capable for 6 sigma, but maybe it will be capable for 5 sigma or 4 sigma. Okay, maybe when it is equal to 1, then this process will be equal to capable for 3 sigma. So these are basically the indicator which will tell us that the data which you have collected, the sample which you have collected so far is capable or not. So these are the things. This is 1 sigma. 1 sigma means that in 1 million 317,000 parts will be defective. You can see 31% production will be defective if we consider the production example. 2 sigma showing, so this is mean plus 1 sigma, mean minus 1 sigma. So this whole area plus 1 mean plus mean 68%. This area will be 68%. So 1 minus 68 point something will be 0.33%, 0.31. So mean 0.3% area will be lying outside. Its mean in million it will be 317,000 parts will be defective. Okay, if we consider 2 sigma, so this is 2 sigma now, plus 2 sigma and minus 2 sigma. So you can see that in 1 million and 10 lakh 45,500 parts will be defective. Similarly, in 3 sigma level, if we want to maintain our quality up to the standard of 3 sigma, its mean the defective parts will be 2700 in 1 million. In 10 lakh 2700 parts will be defective. And for 4 sigma, so 4 sigma mean x plus 4, x minus 4. So its mean 63. So this is also a good quality standard. 63 parts will be defective in 1 million. So it's very good standard, because in 10 lakh particle, if you producing 10 lakh product, so there are only 63 product are defective. Similarly, 5 sigma, in 5 sigma, its mean 6 parts per million will be defective. So this is an advanced level of 4 sigma. So and in 6 sigma, this will be near to 0. Its mean you achieve the high target, the good quality product, because in 1 million there will be 0.001 part per million will be defective. So specifically in Pakistani firms, they totally using 3 sigma. They are in the good organization are in 3 sigma and 4 sigma, because in order to achieve 6 sigma you will spend a lot of money. So maybe your cost will be very high in order to maintain this. So I hope that you understand in this example that what is 4 sigma, what is 2 sigma, what is 3 sigma, and what is 6 sigma. And these are basically the values of CP. So if you are using 1 sigma, so in 1 sigma, it's mean x plus 1 sigma, x1 minus sigma, your CP value will be 0.33. And how you will calculate CP? Upper specification limit minus lower specification limit divided by 6 sigma. In 2 sigma, your value will be this. In 3 sigma, you will meet the process capability, mean your process is capable for 3 sigma. But if you going below, it's mean your process is not capable. For 4 sigma, this value will be going up. For 5 sigma, so for 6 sigma, it will be 2. So that is why in the previous lecture, when we calculate, in the previous example, when we calculate CP, our value is 2.2, which is mean the process is capable for 6 sigma. Okay, so in this way you will calculate the specific process capabilities. So now, in order to use the standard descriptive statistic, I am just going to discuss another example. In this example, I will be going to use that how you will calculate that a specific area is outside from the normal distribution, and how you will calculate. So in statistic, in probability, in the normal distribution, we have already calculated such like things. Based on the normal distribution, the portion of product that would fall out of specification can be calculated. This is best explained using an example. Assume we have a process with mean, so mean is 50. The mean of the process is 50. So if I sketch a normal distribution, so the mean will be the mean will be 50. So this is my mean. The standard deviation is 4. And the upper specification limit is 58 and lower specification limit is 46. We divide this problem into 2 parts. First, the percent out of specification on the height and greater than upper specification limit, and then the percent out of the low end. So now we want to know that which area is inside in the specification limit and which area is outside, and how much percent outside the area lies from the specification limit. So you people know the standard normal distribution. Standard normal distribution is x minus mu. So this is the general standard normal distribution. So now we want to calculate the area outside from the specific limit. So the formulation will be upper specification limit minus mean. So they already mentioned this mean, and standard deviation. The standard deviation is 4, and this is upper specification limit. Z is the number of standard deviation, and you people know when we transform normal distribution to standard normal distribution, then this line is Z and the mean lie at equal to 0, and the mean of the distribution is 0. Z is the number of standard deviation that the specification is from the mean. Normal probability table give you the portion of the distribution that would exceed the specification limit for a given Z value. Remember that 68.3% of the data is within plus minus 1 sigma. So you can see between this plus minus 1 sigma, 68% area lie, and we have already calculated 1 minus 0.31 is equal to 68%. So 31.7%. That is why if you change this into the percentage, it will be 31.7% outside of the plus minus 1 sigma. So now we want to calculate this area, that how much area is lying outside the specification limit, because they already mentioned these upper and lower bound. Upper bound is 58, lower bound is 46, and this is my mean, and this is my standard deviation. So let me put this upper specification limit is 58 minus the mean is 4 divided by standard deviation, which is 4, and 50 which is the mean x bar, minus lower specification limit is 46 divided by 4. So we will get two values. One will be 2. So Z, for Z we will get 2, and this will be 1. How? 58 minus 58, 8 divided by 4 will be 2, and 50 minus 46 will be 4, 4 divided by 4 will be 1. Now Z is equal to 2 for the upper specification and 1 for the lower specification. As Z is equal to 2 is 2.8% out of specification. So you need to sketch this, because this is now Z standard normal distribution. Mean will be lying at 0, Z is equal to 1, and Z is equal to 2. We have already calculated. So this area lying between, this is the capable area. Now we want to calculate the outside area. How much is it? So if you know the use of Z table, so now I am showing you that how you will calculate these values. Z is equal to 1 and Z is equal to 2 while using the standard normal Z table. So now I am just going to show you the use of this table. So this is standard normal probabilities table. So basically we are looking for the Z is equal to 2. So Z is equal to 2 because in the first column these are the Z is equal to 2 values. So Z is equal to 2, which is 0.9772. So you remember this value, 0.9772 is the Z is equal to 2 value, and the other value of Z is equal to 1. So for 1, how much area will be? 0.8413. So for Z is equal to 2 is this one, and for 1 is this 0.8413. So while using this table, we will be able to calculate the area, that how much is inside and how much is outside. So while using these values, so we have already calculated from the table, Z is equal to 1 is 0.8413 and Z is equal to 2 is 0.9772. So the total area is 1. So 1 minus 0.8413. So 1 minus this area for 1 is 0. So we will get 15.9%. So this is area is 15.9%. The total area is equal to 1. For Z is equal to 2. The value in the table is 0.9772. So 1 minus 0.9772. So 2.82% area is on the right side and 15.9% is on the left side. So adding these two, 15.9 plus 2.28, it will be equal to 18.1%. So the total percent expected to be out of specification would be 18.1%. So at this way you will calculate the area, how much is inside the specification limit and how much is outside. Then we will use upper specification limit. Let me show you that now in this example I want to calculate the CP value. So CP as the formulation of CP is, as we already calculate this, upper specification limit minus lower specification limit divided by 6 standard deviation. So just write the formula, upper specification limit minus lower specification limit divided by Six Sigma. So just put these values. Upper specification is 58 minus 46. 6 into standard deviation is 4. So when you simplify it, the value will be 58. So when you calculate CP value, it is equal to 0.5. So in the previous slide, I have already shown you 0.5 mean it not meeting 6 sigma. It's not even this process not mean 3 sigma, and even this process not meeting 2 sigma. It lying between 1 sigma and 2 sigma. So mean the process is not capable for 2 sigma, for 3 sigma, for 4 sigma, for 5 sigma, for 6 sigma. It's only capable for 1 sigma. So if this is the quality of the organization, it's mean they producing 317,000 parts defective per million. So this is not a good quality standard. So at this way you will calculate that the process is capable or not capable. So as I already mentioned, that process capability, basically we want to know the tolerances level. Natural tolerance process spread of a process is the given range that the process can maintain during ordinary operation without the action of any person in making process adjustment. Normally plus 3 minus sigma limits 6 sigma. So now because as I already mentioned, the quality standard starts from 3 sigma. So when you going up to 4 sigma, 5 sigma and 6 sigma, your quality will be automatically improved. Now, how do we know a process is capable? So I already discussed this. Now I'm just going to talk about a little bit about CP and CPK, statistical process indices. So basically these indexes tell if the process is capable of producing feature within the engineering tolerances. This is essentially a grade for the process where the higher number is better. So as I already mentioned, when these values are more than 1, so we will consider that we are maintaining the quality, the process is capable. But when these values are going down, then we will say that these two values, the values of these are lower than 1, so they are not meeting the standards, they are not meeting the quality standard.